Hello, welcome to this video. So this video is going to be rather brief. It's essentially talking about what it means to formulate different models within physics and how we can express the same physics using different kinds of models. This is quite interesting because sometimes thinking about a problem using a different type of physics or a different focus of physics might really help make the problem a lot simpler. Also, different approaches are geared towards different things, and so having a wide variety of approaches is quite helpful. And this video will be about explaining how you can have different approaches with different kinds of mathematics, which lead to the same thing ultimately. So how to formulate physics in new ways. So I'll be using a couple of examples, firstly classical physics and then quantum physics. So with classical physics, there are two main ways to solve things, at least to do with classical mechanics. These are using the Lagrangian formalism and using Newton's ideas. So Lagrangian ideas concern energy. They're about kinetic and potential energy. And if you know the kinetic and potential energy of a system and how to write it in terms of variables like position or velocity, then you can use the Euler-Lagrange equations to actually derive the equations of motion for that system. And this is very, very useful if we're dealing something where there are lots of very complicated forces. It's very good for demonstrating certain conserved quantities because you have something called conjugate momentum, and conjugate momentum is always conserved. Sometimes it's called generalised momentum, but the point is you get conserved quantities falling naturally out of the Lagrangian formalism, whereas in Newtonian mechanics you take that those things are conserved for granted, and using this and forces and such, you work out the equations of motion. The thing that kind of links the two, and why they can both be applied even though they seem very different at first, is because force and energy are closely related. I mean, if you think of kind of work done, that's essentially the energy gained by moving, by accelerating an object in a particular direction, or in other words, applying force in a particular direction. So energy and force are very interrelated, so it's natural that if we can solve something using ideas of forces, we can solve it using ideas of energy. And then the next thing to look at in terms of formulating physics in new ways is the Schrödinger formalism for quantum mechanics vs Heisenberg's formalism. So in Schrödinger's formalism, the wave function is represented as a complex function, and the wave function is a continuous function. That is associated with the probability of that particle being at a particular location. Whereas in Heisenberg, you do exactly what you do with functions, but with vectors and matrices. And the reason why you can do these things, and why Schrödinger and Heisenberg both can be applied to the same thing, is that ultimately functions as well as vectors and matrices all belong to a vector space, and therefore can all be treated generically using ideas of linear algebra. So linear algebra really relates these two formalisms. So use Schrödinger formalism if you're looking at kind of finding the probability of a particle being at a particular position, be that in a simple harmonic potential well or in a finite but, infinite well. Whereas you use Heisenberg formalism more so when you're talking about things like a particle which is in superposition of two eigenstates, or when you're talking about things like the uncertainty principle, or things like that. The Heisenberg picture is quite useful, or spin. So when you're talking about certain quantum numbers again, Heisenberg formalism helps there. So this has been rather brief, but this is just a video to help explain how you can have completely different physics at first, it might appear, help to derive the same things, but where one might be stronger than the other depending on what you're thinking of or considering. And really the point of this video is to show you that physics isn't, cut and dry, this is the way to do it, but there is nuance and flexibility within physics and within the mathematics we use to describe the universe. I really hope that this has been a good video. I know this has been fairly brief. I'll be working on creating more stuff, particularly more satanic things, but I really hope that this has been helpful nonetheless. Thank you for watching, and hopefully see you for the next video.